So we have seen the floating point representation. The need for floating point representation is, of course, uh, everyone understands the need to work with very large magnitude numbers as well as very small magnitude numbers, particularly when we are dealing with a machine which is finite in size and it cannot represent uh, infinite digits, right? So within a finite size of representation, we should be able to deal with very large numbers and very small numbers for all practical purposes. And for that purpose, floating point representation uh, was devised, and binary representation, binary encoding is of course used. And by virtue of that, the standard floating point representation for binary number system, the whole part can only be 1, and therefore that 1 is never stored. It is always assumed to be there, and the standard format is plus or minus m0, that is the whole part of the mantissa. This is the separator between the positive exponent and negative exponents, and these are the fractional bits m1, m2, m3. These are the fractional negative exponents of the base, and multiplied by beta is the base of the number system, and raised to the power e, that's exponent. So when the requirement for standard representation for floating point numbers is m0 should be greater than 0, and it should be less than the base of the number system. And for binary number system, the choice is only 1. So the number will always be 1 point, whatever bit pattern you have for the fractional part, multiplied by 2 raised to the power whatever exponent you may have. So when the standard representation requires the whole part to be always 1, we choose to make it a standard and avoid storing it altogether. So all floating point numbers, they are assumed as 1 point something, and while storing only the fractional part. Very clever trick to get 1 bit of extra accuracy. The offside being number 0 is not representable. We can have a very small number, but we can never have 0 as a result of floating point computation, right? Second point is the exponential representation. The magnitude increases with integer powers of 2, right? This number 2 raised to the power e. So e is an integer. So this magnitude of the number increases or decreases in integer powers of 2. So this is an exponential distribution. The separation between, I mean, just look at the numbers. Let's look at the integer power of 2. 2, 4, 2 square is 4, 2 cube is 8, 2 raised to the power 4 is 16. Just look at the differences that you have between consecutive powers of 2. First 2 and 4, then 4 and 8, then 8 and 16, then 16 and 32, then 32 and 64. As the magnitude increases, adjacent, the space between two neighboring numbers increases, right? And these two neighboring numbers are the numbers that are exactly available, that are exactly represented on the computer. Anything in between is not available, right? The floating point representation cannot understand anything in between. Anything in between these two distinct neighboring numbers, discrete numbers, right? So they will be interpreted, they will either rounded off to lower number or rounded off to higher number depending on what rounded round of strategy in place. But the point is, every floating point operation, given the our understanding that real number line is infinite, any operation with real numbers can be anything. Possibility, what is the probability that you will generate or you will come across as a result of computation a number which is exactly represented on the computer without any round of error? It's zero, practically zero. So every floating point operation incurs round of error. It is a source of error. And this error keeps on accumulating, right? So the algorithm design becomes very, very important. If the error is of systemic nature, that errors of only one sign are being accumulated, then it will cause a systematic drift, and your result would be uh, useless after some time. That is what we saw in the failure of Patriot missile system. The case study that I shared with, which was compiled by Nick Higam, right? 1991, there was a Patriot missile system deployed in Saudi Arabia at Darhan Air Base, and it failed to intercept incoming Scud missile fired from Iraq. And that was because of the drift. It was in operation for a long time, and accumulating the systematic error of same sign, uh, it could not track. It was completely out of range. So algorithms need to be designed such that floating point errors, whenever they occur, first they should be of small in size, small in magnitude, as small in magnitude as possible, and they should be random. I mean, you should incur floating point errors of both signs. Sometimes they may be positive, sometimes they may be negative, right? And then the chances are, over a period of time, over a sequence of operations, those positive and negative errors would uh, tend to offset each other, and you would still be ending up with a usable result. So how do we make the round of errors small? That is a given that every floating point operation is a error prone operation. It contains, no matter what you do, it will incur error. The best you can do is make the size of error small. How can you do that? The clue lies in what I started this discussion with. The distribution of numbers is exponential. Let us look at integer powers of 2. Right? Let us plot it on number line. So this is 0, 1, 2. So this is 1, 2, and then 4. Then you have 8, and then you have 16. Right? Now you look at, this is how roughly this represents how the numbers are stored in your computer, floating point numbers. There may be some more numbers in between, but broadly this is how they are arranged. The important thing to notice here is the exponential distribution or logarithmic distribution, whichever way you look at it, right? And the important thing that you should notice here is the spacing between the numbers increases. Two adjacent numbers increases as the magnitude of the number increases. So if the result of your computation happens to be somewhere in between, it will incur larger round of error rather than if your computation results into somewhere in between here in this range, right? So the first key is before you perform any operation, floating point operation, first thing to do is scale the numbers to a small magnitude range. Numbers are represented as m0, point, m1, m2, m3, 2 raised to the power some exponent. Magnitude depends on only this exponent field manipulation, isn't it? And that's integer arithmetic. If I scale it by, let's say, beta raised to the power alpha, alpha is an integer. What is the magnitude? Okay, not beta. Okay, we are using 2. So 2 raised to the power alpha, that is some scaling factor. Alpha can be integer, positive, negative integer, whatever, according to the need. So this number is equal to m0, m1, m2, m3, 2 raised to the power e plus alpha. That's an integer arithmetic, and that is performed exactly as long as we do not incur that carryover. We do not exceed the range of integers in the machine. But otherwise, this operation is exact. But by doing this, I can make this number, original number, small in magnitude wherever required, whenever required, and then perform arithmetic on this. So when I perform arithmetic on this smaller magnitude number, I incur smaller round of error, right? So essentially the operation would be two times. Once I need to scale it to the lower magnitude number where the density of machine numbers is more, so that I incur less round of error. And then after I have computed this, then I need to scale it back to the original number. I need to negate that scaling operation, right? So so this is essentially the basic principle or basic care that you need to do, that you need to take while designing algorithms for any computation, numerical computation using computers, digital computers. If you are not careful, you may incur such large round of errors that your results would be practically useless, right? And what use it is to say that this result is being computed from a very expensive digital computer and that result is completely useless, right? So the value or quality of result depends on how are you computing it, and that is why design of algorithms and translation of those algorithms into robust computer programs is a very, very important skill. Right. So concept of hidden bit we discussed, and there are two representations: floating point representation, single precision, based on 4 bytes. So 32 bits in all, and out of those 32 bits, one most significant bit, first most significant bit is the sign bit. Next 8 bits are the exponent field in XSK notation, right? So that's a biased representation offset, and rest of the 23 bits are the fractional part of the uh, mantissa in base 2 number system, base 2 representation, and including one hidden bit, you get 24-bit precision. And if this is not enough for the accuracy that you need for your computation, you have another more precise number representation that is exactly double of what you have for single precision, that is double precision, identified by the keyword double, and that is comprises of 64 bits in all. So just double the single precision word length float type. So double is 2 times float, so 64 bits, and out of those 64 bits, again one bit is reserved for sign, the MSB. Next 11 bits are for the exponent field, and then remaining 52 bits are for the fractional part of mantissa. And using hidden bit, again you can increase the precision to 53 bits of effective precision. So normalized exponential floating point representation is an exponential distribution in powers of 2, and with the slightly unusual result byproduct that the numbers are distributed in exponential distribution. They are not uniformly spaced. This is what our mind naturally assumes. When I am given a range of numbers, unless otherwise specified, my first urge is to assume those numbers to be uniformly distributed, right? But that is not so on a computer, on a digital computer. Those numbers are distributed exponentially, and therefore the difference between two consecutive numbers can be very, very different depending on the magnitude of the number. Small magnitude numbers are more closely spaced, large magnitude numbers are very sparsely populated. And the direct implication being, if you perform operations, numerical operations on numbers with magnitudes very large, the chances are your computations are going to be completely useless because of large round of errors that you will incur. So the key to robust computation is, first, scale the numbers to small magnitude range where the magnitude of round of error is much smaller, and after the computations are over, scale it back, negate the scaling operation, reverse the scaling operation. And the use of hidden bit prohibits representation of 0 in floating point representation. So you cannot compute 0, no matter how expensive your computer is, how powerful that computer is. Doesn't matter if it ranks 1 in the list of supercomputers of the world, it still cannot compute 0. So these are the essential parameters of floating point representation. Single precision has 24 bits precision, and double precision has 53 bits of precision, including hidden bit, of course. The exponent ranges from, 8-bit exponent field in single precision gives you the range of integers from -126 to +127, and for double precision from -1022 to +1023. And exponent bit is of course 8 and 11. And total format width, word length as we call it. So for float, one number occupies 32 bits, and for double, one number occupies 64 bits in all. Now there are two spatial, or rather four spatial representations that have been defined in the standard to take care of spatial situations. As I said in the beginning, number 0 cannot be defined. Standard floating point operation does not have any representation for 0. So if I define a variable, let's say float x, and I initialize it to a value of 0, 0 is a valid number to be initialized, right? So what bit pattern will it take? So that is an arbitrarily assigned bit pattern. That is, all bit fields are 0, all fractional fields are 0. Right? So if all 8 bits in single precision arithmetic, all 8 bits of exponent field, they are 0, and all the fractional fields, 23 bits of fractional fields, if they are 0, that is interpreted as 0. Right? Again, this cannot be arrived at, this particular arrangement cannot be arrived at through computation. This can only be assigned. When you assign in number 0, value 0 to any variable which has been declared float or double, all all bits in that word would be set to 0, would be initialized to 0, and that is what it is treated. Right? And sign bit again can be either 1 or 0, so you can again have representation of either positive 0 or negative 0. Right? Depends. That's a random data. So what happens when fractional field is not 0? So that is a placeholder we assume for that spatial representation when exponent field is all 0 but the fractional field is not identically 0. We consider that to be equal to a spatial representation where the whole part is 0. So the number is interpreted as 0.f, whatever is the fractional field that corresponds to, multiplied by 2 raised to the power the minimum exponent field. Right? So minimum exponent field would be whatever is the minimum field that is specified in the standard according to that format. That is different from what we discussed here. Right? So this is -126, and E min -1 is what is we are referring to here. So 0, 0, 0, 0, 0 is actually 1 less than this. Right? So actual distribution, if you look at 8 bits, variation of 8 bits, what is the total representation? 2 raised to the power 8. What is that number? 256. Right? So if you divide 256 into plus and minus, you would get it from -127 to +128. Right? So where have these two gone? I am referring to whatever is the maximum power exponent is +127. I am neglecting, I am not counting 128. And here minimum is minus 126. I am not counting 127, minus 127. Minus 127 corresponds to all zeros, all 8 bits being 0, and 128 corresponds to all bits being ones, right? So these are two extreme positions, and that is why uh, we are referring to here this as E min minus 1. So minus 126 minus 1. So that is minus 127. Minus 127 corresponds to all exponent bits, 8 bits being 0, right? And the number being interpreted is 0 point whatever is the fractional field multiplied by 2 raised to the power minus 126 E min. That is precision. Precision. 23 bits are the fractional digit plus 1 hidden bit. So you get 24-bit precision in single precision and 53-bit precision in double precision. Oh, it follows from this. See, that's a standard representation, isn't it? For out of these 32 bits, 1 bit MSB is for sign bit, 8 bits are for exponent, storing the exponent range, right? What are you left with is 23 bits. So 23 bits are the fractional field plus 1 hidden bit, that is 24th bit. So your number, significant digits in the number, they are defined by these 24 bits, right? So that is what the precision means. 24-bit precision, that corresponds to about 7th place of decimal in decimal conversion, equivalent decimal number. So your numbers are significant. The number of significant digits are up to 7th place of decimal. Beyond 7th place of decimal, it's all random number. It doesn't matter. And for the double precision arithmetic, double precision or double precision number, double type, the numbers are accurate, or the significant digits are up to 14 places of decimal. Beyond 14th place of decimal, those are just random bits. Those do not have any significance, right? I mean, you must have come across this business of significant digits in computation. I mean, what is the least count of your scale measurement? Linear scale, 1 millimeter, right? So that's uh, that is the smallest value you can resolve. So anything less than 1 millimeter, talking about anything less than 1 millimeter doesn't make sense. Using that scale, that does not mean that measurements do not exist which are smaller than 1 millimeter. It's just that you cannot resolve it using that device, using that scale, right? So it is the same thing. So you have precision only about 7 places of decimal. Anything beyond 7th place of decimal is just random. You do not have any business to talk about it. I mean, you don't know what is happening beyond 7th place of decimal in single precision number, right? Similarly, you do not have any idea about what is happening beyond 14th place of decimal. Magnitude may be very large, right? The number may be as well, I mean, 10 raised to the power 30 or so. So that is the magnitude. But when you are looking at the precision, you are sure only about 7th place of decimal or 14 places of decimal. Beyond that, you have no idea about the precision of digits, right? So these are called, this special representation is called subnormal, and that is only one attempt to make use of this representation. These numbers are obviously less precise than standard floating point numbers, and that is why they are called subnormal, right? So these are not to be used, I mean, not to be taken seriously. It's just be aware that there is something called subnormal representation for this spatial representation. We generally do not make use of that because these numbers are not as accurate as standard floating point numbers. They incur significant loss of precision. Just to take you to the extreme, take the case where all 22 bits are 0 and you have 1 only in the 23rd bit LSB. So that has a precision of only 1 bit. It has a precision of only 1 bit compared to 24 bits of precision of standard floating point number, right? So this subnormal representation is not really of any significance in numerical computation. It's just there to make use of the space. Then we come to the other end. When the exponent field is all ones, right? So that corresponds to plus 128 integer value, positive integer value of plus 128 in single precision number. And if the exponent fractional field is all 0, all 23 bits are 0 or 52 bits are 0, the number is represented or taken to represent plus or minus infinity depending on the sign bit. So again, this is an assigned representation. As I have been maintaining all along, computer is a finite machine. It cannot represent infinity. So here, this is a spatial representation which is an assigned representation of infinity. And any number which is computed to be beyond the range of numbers, available range numbers, it is simply assigned this infinity, depending on the sign whether it is plus or minus. If it exceeds the range, it is assigned this infinity number. So that is how this infinity business is taken care of on this digital computer, on this finite machine. Then that leaves us with another spatial representation where all the exponent bits are 1 and fractional bits are not identically 0. There may be 0 or 1. Some bits may be 0, some bits may be 1, or all may be 1, right? So it is not identically equal to 0. That represents, this representation, this bit pattern stands for again a spatial condition that is called not a number, NaN. NaN represents or it signals an invalid operation. An invalid operation such as division by 0, right? Unintentional division by 0. It may as well equally be interpreted as infinity. But trying to compute logarithm of a negative number, that is an undefined operation, right? So how do you, if you, I mean, let's say if you write a code where you need to compute logarithm of some variable x, and x is being computed by some other process, and when you encounter that statement log of x and x happens to be a negative number, how do you compute that? That operation is not defined and the result would be promptly assigned NaN, right? So just to alert the user, and any subsequent use of that result will also result in NaN, not a number. And similarly, any subsequent use of infinity would result in infinity, right? So that the programmer is alerted that something has gone wrong or what has gone wrong, some indication. Yeah. 256. We have left two. I mean all zeros and all ones, and then two two configurations for exponent field and two possibilities for the fractional field. Fractional field all zeros and not zero. Right. So together these they make us present us with four possibilities, and those four possibilities are listed here as special representations. It was just a placeholder, so I mean it is there, so let us make use of it. Why let it go waste? But it is a waste. It is of no use at all. So this is how the exceptions are encountered and handled. Various exceptions: overflow, the result of computation exceeds the range of numbers that can be represented, floating point numbers. Integer overflow, it happens, it is promptly rolled back into the range. You will not even know that overflow has occurred. But for floating point operation, if the overflow happens, the number is computed which is beyond the range that is represented, that can be represented, it is promptly assigned plus or negative infinity depending on the sign of the result. Underflow, result is too small than the smallest number that can be represented. So the result is reported either as subnormal number, which obviously is going to be smaller than the smallest 24-bit number that can be represented on the computer, or just assign it to be 0. It is smaller than the smallest number, let's call it 0, right? So again, that's a special field. You just assign it to be 0. You are not very sure whether it is 0 or anything in between, right? You just call it 0. Divide by 0, it is interpreted as infinity, plus or minus infinity. Subtraction, addition, operations between two infinities, not defined. Logarithm of negative number, not defined, right? Square root of negative numbers, not defined, unless you are making use of special representation of complex numbers or complex family. But floating point numbers in the arithmetic itself, square root of negative numbers is not defined, right? So impossible binary to decimal conversion. And as I said, every floating point operation will incur error, will incur some round of error, and that round of error would be, and the result reported is only going to be an approximate, whatever is the exact machine representable number, nearest machine representable number, nearest or smaller or larger, whichever round of strategy is in force, right? So summarizing again, what are the limitations? Floating point operations, floating point representation give us enormous power to deal with a very convenient, uh, deal with very wide range of numbers in a seamless manner. We don't have to worry about whether the number is as small as 10 raised to the power minus 33 or as large as 10 raised to the power 39. Right? I don't have to worry about it. The standard takes care of it, and all representations are in place, properly handled. Provided that I take care of round of errors and error propagation in my algorithm, and whenever before performing any computation, before performing any arithmetic operation, I take care of proper scaling and then scaling it back. things should be fine. But you should understand, you should keep in mind that only a finite set of discrete numbers can be represented exactly on the computer. And the probability that your computation will exactly coincide with these numbers is practically zero. So every floating point operation will incur round of error. And these available numbers, exact machine numbers, they are not distributed uniformly. The spacing is logarithmic. Where else do you see logarithmic spacing, by the way? Mm-hmm. Louder? I didn't get pH scale. Okay. Beyond science. I mean, I just want to make the discussion a little more interesting so that you can begin to appreciate the beauty of what we are discussing. I mean, it is a very, very fundamental, very, very, it, it is not dry mathematics. It operates at a much higher level. Anyone remembers how does sitar look like or any veena looks like for that purpose? Ever notice the spacing of bridge on those sitar, those instruments? How are they spaced? That's logarithmic spacing. And that is because, I mean, everything is frequency. Those musical scales, those are based on octaves, right? One octave differs from second octave by a power of 2. Those bridges indicate the octaves, different scales, right? So look at, next time you look at sitar or veena, rudra veena, you will find precise logarithmic distribution of those bridges, right? So coming back to numbers. So mathematics is not all dry. It's music. It's musical. So greater round of errors in computing with large magnitude numbers, and therefore scaling of numbers is often necessary to operate in the small magnitude range so that round of error that you incur is smaller. And then of course you need to maintain the sanctity of the magnitude. So once you scale it back to small number, after operations you need to scale it back to normal magnitude. But the round of error would be under control. Normal laws of arithmetic, because of this round of error, normal laws of arithmetic may not hold. A plus B plus C may yield different results depending on whether you first A and B and then add C, or whether you first compute B plus C and then add A, right? The sequence of operation may incur different round of errors. So final result may be different. The only thing I am saying is it need not be different, need not always be different, or need not be obvious to you. Need not be obvious to you in that significant digits, 7 places of decimal, right? But it is quite possible that what you take for granted as associative law or distributive law, they may not hold while working with computers, right? So choose a form which will incur less of round of error, whichever form, right? They are not identical. They will not always give you identical results, different things, different forms, which we take for identical as granted. Okay, so programming, taming the beast, and I stop here. My time is up. We'll continue on Monday. So any questions?